Hey, welcome to week 2. So first, let's review last week's homework. Hope last week's homework isn't too complicated for everyone. We will go through some of the solutions, see what there are a lot of solutions right, for those problems. Let's just see you. There are some solutions that are easier and they're not. And that bring the topics up for today. How do we measure programs efficiency or complexity? So there are two dimensions to the efficiency of the program. One is on the time, whether how fast can it run for the problem. It's a measure is called a time complexity. And there is a big O notation to measure the time complexity. And then similarly, there is also a space complexity. So for any program that want to measure how efficient a program is measure the time and space complexity. Then we go through some of those examples as well as some common complexities classes in especially for those problem that we're aiming for to solve for USACO problem. Okay, so let's take a look at the homework first. So the first problem on the basketball, so I thought most of you that actually follow this problem, right? Given the string, calculate the score for each player, A, B player. So based on the string, like given each string, calculate the score. Then you determine the winner. So I think that's probably most of you do that. But if you look at this problem, there is a pattern, right? It only asks you determine who is the winner. It doesn't ask you what's the final score. So you don't really care what's the final score. You only care who is the winner, right? If you look at the score, the last player's score, right? If you look at just the last player's score, must be the winner, right? So regardless of how it end up with the before it, the last person, if this the score that ended, the last person just scored a basket, must be the person win the game. So so if you find this one, right, given any string, just look at the second to last character. What's that? Whether it's A or B, then you determine the winner. So the solution is as simple as this, right? You're reading this string, you do this, right, string this is 5, and then -2. So from that, just output that character. Any question on this solution? So there is no need to go through the entire scoring pattern. Just look at what's the second to last character. Okay, number 2, the weird algorithm is just a pattern given a number is go through checking, see whether it is an even number. If it's an even number, then divided by 2. If it's an odd number, then multiply by 3, then +1 all the way until it is 1. Right? So it's just need to check whether a number at any given point it is you go through it, you have the condition whether it is 1 or not, the number. If it's 1, then you stop. Otherwise, you just keep going a loop. So you can just using a while loop, right? Check what's the number and stop if it's a 1. If not, then you check whether it's even. If it's even, divide by 2, or you multiply by 3 plus 1. It's can everyone hear me? Kenny, can you hear me? Kenny,
Yes.
you can hear me? Okay. So Joel, okay, then it's Joel's your audio's a problem. So Joel, if you cannot hear, I would suggest you just exit and rejoin the meeting. And so, and also for this problem, you don't need to store the whole sequence of the number. So I see many of you, the solution store this whole sequence in a vector when you calculate each number. If it's not one, you just push back to the vector. Then when it's one, then it's done. Then you print out the whole sequence, right? So although that is fine, but it just take more space. As you calculate each intermediate number, just output it, just do a C out, right? It's just output. You don't need to store the whole sequence. Just output each number. So here is my solution. So we just need to, this could be a big number, as I said, just use a long number, right? So use a long number and read this input number, do a while loop when it's not one, then just output this number first, right, with a space so that you know what's the next number, and then check if it's even, divided by 2, else multiply 3 plus 1. And so this while loop, you just output this intermediate number as well. And then at the end, when it stops, this will be 1, right? You need to make sure that you output the last number, which is 1. So any question on this solution? Okay, last problem is the USACO train problem. So it is giving you trying to calculate those number with, and then with it, it is a mass 47. And so you just need to, so first of all, so all those older USACO's problem, the input is in a file, and then they expect you to output a file, right? It's specific, the file name given in the problem. So write.in and write.out. So those are the file names. And then you define those file name, then you do the IF string and OF string for those two file name. Then you can use F in and F out, just like a C in and C out, right? So you first read in the group name and the comments name. Then you, this is checking convert the alphabet, right, the character into ASCII code. So you calculate from relative from A, right, with the relative number from A. So getting a character using an int, and you convert that into ASCII code. Then for each character in this group name, you calculate this relative to A, giving the number, this A's number, right? It's a good number, and then you do a product. And similarly, you do the comments in a product. And when you're done with calculating the product of those converted ASCII number, then you do a mass 47 on each side, see whether they are equal. If it is equal, you go, otherwise you stay. So for this problem, so as you walk through solve others USACO problem, so the beginning, so probably will be very similar, right? Reading the file into an IF string and OF string, and then it's just a matter of how to store those numbers, read those numbers in and store them, do the calculation, and then do the output. Okay. If no question on the homework, let's move on to today's topic, efficiency. Okay. So in the competitive programming, efficiency is very important. If you write your program and it run a long time, then it exceeds the time limit. For USACO's problem, all the problem, the limit is 2 seconds for C++ program. Same for Java. I don't recall what's the Java. I think Python, they get double, get 4 seconds. But even Python program, 4 seconds, it cannot come half the speed of C++. That's why the majority of the students participate in just USACO using C++ for this speed. And also, this is 2 seconds is just not necessarily on your own computer. You may have a computer that is faster than the one, the grading computer, which is hosting on it could be a very old computer. It's the 2 seconds on that old computer, the grading server. So how do we measure the efficiency in terms of the computation time? Right. So that's what's known as trying to people study all the computer programs efficiency, come up with this idea called a big O notation. Right. So this is trying to come up with a scenario for any given problem, right? You have an as an input, right? So input n, as n become bigger and bigger, and then see how much time, the runtime, as a function of this input, right? So all those problems, the n could be the number of elements in an input. As you deal with more elements, then obviously it will take more time. It's just the incremental as n become bigger, how much time that you need to get in order to solve. So it's trying to plot the relationship between the input n and your runtime. That's measured in this function. Right? So in this function, there's called as a big O notation. O is a function, so that is this function could be very complicated, right? When you're using the big O notation of this function of given the input, what's the runtime? Trying to simplify into a few classes of function, right? So that any constant factor, then it doesn't matter. Just get into the a very large case. So just looking at some example, right? If you look at some of those assignments, if there is no loop, just a single statement doing the calculation, it's just one time run. This big O, then it's O1. So O1 is the most efficient operation, right? It doesn't involve any loop. So it doesn't depend on n. N has become bigger, then the runtime stay constant, stay the same. It doesn't increase. So O1, that is the most efficient algorithm. If you can design an algorithm doesn't involve any loop of the input variable, that is the most efficient. O1 is the most efficient. And then the next level is when you need to do a one-time loop through each element of the input variable n, right? So given an n, so this is a typical, you need to go through each element of this is whether it's an array or other um, dynamic structure has multiple elements that you need to go through each of them, iterate through. Then assuming inside this for loop, this is O1, so this is only constant code. So you are not doing any further loop inside. Then this whole for loop is ON. Right? So this is ON. And similarly, a while loop is very similar to the for loop, right? You go through each element and assuming you have your code here, this block doesn't involve another loop, just doing the constant calculation, then this is also, this block is also ON. So those are very common O1 and ON. And then you get into a nested loops situation. You have a matrix you need to go through, right? It's just one loop, it's not efficient. You need to go through each row, and then within each row, then you have multiple element as well. So it's like a matrix, right? You need to go through row and columns to traverse each element. So you need to have a nested loop. So this row dimension is n, the column dimension is m. So the number of time, assuming if within this nested loop, this is also no more loop, right? This is a constant, just doing calculations, doing an O1 type of calculation. It doesn't matter how many of them inside, right? You could have a million lines in here, as long as there is no loop, that's still O1. Right? So it's O1 is not just a one operation. It could be a lot of operation, but as long as you're not going through a loop going through that, depending on an input parameter, then it's still O1. So we think this is O1, but it's in the nested two loop, then it's the product of this number of times you're doing the loop. So this outside is n, and then inside is m. So you multiply the whole example is O m n. So any questions so far? So we learned O1, ON, and OMM, the product. And when this m and n, they are the same, will become what? It becomes n squared, right? If this number is like a square, the matrix, you have number of rows and number of columns, they are the same, right? You loop through the same number of time in this nested loop, then this big O notation measure the complexity is O n squared. Okay, how about we have some other factor, right, in the loop? Instead of looping through n time, we're looping through 3n time. What do you think? So this is big O notation. This will become, let me go through the cam right on this. Need to share a different screen. Is that the right screen? This to be the PowerPoint you see. Right. So for this, right, it would say O3N, right? Oh, but when you this big O notation, O3N, anything that is a constant, it is the same as we can get rid of the constant. So it's like this when we're doing the big O notation, and anything that is a function of n, if this is the same as you multiply some constant, say a, is identical. So if this is a constant, or if you adding another constant, b, b could be a million. It doesn't matter. It's as long as it's a constant, right? It's a big number, but it's still we can get rid of the constant, just like ON. So this Fn could be any function, whether it's n or n square and q. This always true. Okay. So when it's a 3n, then this is just ON. And this n plus 5, then it's still ON. And so those are three blocks. In terms of the time complexity, they are identical. I know it's sometimes it's a little counterintuitive, especially you multiplied a big number, right? This is three times as worse than this one. How come the complexity they are identical? Or if you multiply this constant, it could be a million, right? The constant, but if so long as constant, then well, how come this a million times worse still same as the efficiency as this one? So it's just they are just measured in terms of the magnitude. So it not none the actual runtime they may be different, but in terms of in the order of the magnitude they are identical. You will see it later on, right? This is what is known as a polynomial. Anything that is a polynomial, then is still very efficient, right? Then we get into the non-polynomial, then it's just getting much worse. Okay, let me still go back to share the right screen. Right. So this for any constant A and B, so this is the identity. This is always true. So n is a variable, but A and B are two constants. So it has a factor of A or plus a constant. This is still true. Okay, what about a block of code that has a multiple step? How do we measure the complexity of a code that has multiple steps like this one? Right, the first step, right, this is just a one loop, right? So this is ON, right? And this is second block, it has two loops, a nested loop. So this is ON square, and this is another ON. So together, how do we measure the complexity? Do we say ON plus ON square plus ON? No, we just simplified it, just use the worst case, which block has the worst case, right? So this in the middle is ON square is the worst case. So when Sn becomes bigger, like this middle, then two nested loop will take the bulk of the runtime. And then the other step probably just taking a small amount of time is manageable. So we don't even need to add that because the whole block of code is ON square in terms of the time complexity. Okay, so when you have multiple steps, just look at which step is the worst case. How about recursive function? So instead of loop, we can calculate whether it's a one-time loop or nested loop. But if it's a recursive, how do we calculate the complexity? So when it's a recursive, you can treat it depends on within each function, how many times you calculate the recursively. So this one, for this example, so you have a boundary condition when reach one, you return else, you decrease the input by one at two. So it's calling itself just once. So this essentially you can get into a loop situation. So inside this, there is no loop as O1, but you are decreasing the n until it reaches one. So it is calling multiple time, right? So there's the ON complexity. Okay. So you can rewrite this recursive function using a loop as well. So then the complexity, in terms of efficiency, should be identical. However, I will show that later in an example. You have to be very careful with a recursive function, right? A general rule of thumb, if you can do a loop without doing recursive, that's always the better. Recursive, even though C++ doesn't have a limit in terms of how many times you can call itself recursively, so the depth of recursion, it doesn't have, but it does have a stack of memory to keep track. Those are recursive, and then if that stack is out of memory, your program will stop. Whereas that won't work. There is no magic number like how many times we can recursively call, whether it is 1,000 times or 10,000 times or a million times call itself. Don't know. But when you get into a large number, called recursively a very large number, then the program can fail. I will say later on in an example. Okay, what about this example? This doing twice, calling itself, decrease the input by one, but call itself twice. So it is doing the, so if you think this is just a 2 times the 2n or n square, that's probably your intuition. But if you look at it, how it's being calculated, right? When it's n is 1, then it's 1, then it return, right? That's one time. But if it's 2, then 2, you call this F1 and then F1. right? Number call this function will be twice, right? But when it's 3, you call the F2 twice, but F2 will be 2. So 2 plus 2 is a 4. When it's a 4, then this you call F3 twice, right? Each F of 3 is a 4. The 4 plus 4 is 8. So you can see as n becomes bigger, this grows exponentially. So it's not to the square of n. It is to the 2 to the power of n if you add this together. So this is really, when the n become bigger, this is really get out of the control, right? So you have to be very careful with recursive when it's calling multiple times itself inside the recursive, then it's become an exponential in terms of complexity. All right. So far we have seen some example. Let's just to summarize some of those complexity classes. We already mentioned O1 is the most efficient, but it's a constant time. It doesn't depend on the input side. So as the input n getting bigger and bigger, it doesn't matter. It should run the same amount of time. And the next most efficient one is like we saw with exponential. The inverse exponential is a logarithm, right? Logarithm is as n grow bigger, the logarithm, the log of n, it increases very slowly, right? So it is the opposite of the exponential. It's growing very slowly, even slower than the linear, right? So as n getting a huge number, but log n could be still a very small number. So this is the next best algorithm other than the O1. So O log n. So O1, you probably have to come up with a formula. Oftentimes is some problem that if you need to use a loop, then you cannot do O1. You have to come up with whether it's a mathematical formula that can do a direct calculation instead of doing a loop. Then you can get O1. If you have to do a loop, then the next thing that you're trying to see whether we can design an algorithm in log n. This is the second best in terms of efficiency, log n. Then after that is the square root of n, right? Square root of n is not as good as a log n, but still better than on because it's the square root that grows a little slower than n, faster than n. And but we don't see this square root of n very often. So there is log n. There are some famous algorithm in log n, which we will learn in later part. Probably some of you have heard what's called a binary search, right? When you need to search an array, a sorted array, an element, and using a binary search to find the element that meet the value they're looking for. And that algorithm is the log n. And we will learn the binary search algorithm later this semester. So that's a log n algorithm. And n square, or the square root of n, we'll learn some example not as famous as log n, but O n, you already see just one loop of using a loop then it's ON. This is known as a linear algorithm. It's probably the most common, right? When you have to go through each element in a loop, then it's become ON. So trying to challenge yourself, right? Whether this is probably the most intuitive when you're trying to, you have a multiple element in a list, you need to go through them. Then this become a natural. You use a loop to go through that. That's become an OM. But always think about that, whether can we get into a log n, a more efficient algorithm, or whether we don't have to go through all the elements, just using one calculation. And then after ON, right, you need to get into more of the nested loop situation, right? Instead of doing traverse the element twice in the nested loop, but you using one of the loop more efficient. Using one of the loop is log n. So then this together nested, one is n, one is log n. Then the product of this two nested loop is n log n. So this is still better than n squared, right? So because the log n is increase much smaller than n, so this is much better than n squared. And you will see there are a lot of famous algorithms, this especially with sorting, they are in this category. So n log n, we will learn some of those sorting algorithms. I don't know whether we can do that this semester or next semester. Right? The whole focus, some of those algorithms you will see is more how to design the data structure and the algorithm to trying to achieve the most efficient in terms of the big O notation as much as possible. Then quadratic n square is come naturally in a two nested loop. So this is very common, but this we mentioned isn't oftentimes not the most efficient, right? If we can get into the n log n, you think this doesn't make any big difference, but as n become bigger, it make a huge difference between n squared and n log n. Then n cube, it is, then you need to do 3 nested loop, and it is much worse than n squared. And again, you could check whether one of the loop we can get into a log n type of situation rather than go through every element. And this is probably, this exponential is the worst. When you get into this kind of situation, you oftentimes you get into doing combination type of situation. So for those of you learn the math number theory, that there's a combination. So for every given a subset, and then what are those pick one element or two element or three elements type of situation. That's that. This if going through all the subset of the element, then it can end up with this exponential. And there's something worse than exponential. This is that factorization. Right? If you input and you're doing a factorization, and this is quickly can get out of control. This is essentially when you're doing the factorization, this is getting to the permutation situation. You have to check every permutation, right, for given an array of elements. you have to go through every permutation, then it becomes the n factorial. And this is the worst algorithm. Okay, so we have seen some of those common complexity class. Then within those, and there is called this a polynomial. An algorithm is a polynomial time. Then it is the it's n to the power k, but this k is a constant, so it doesn't depend on the input. So this n n1 or n square and cube, those all belong to this polynomial family. But those that we see the exponential 2 to the power n or n factorial, those are not polynomial, right? Most of those that we have seen, the previous example, they are all polynomial except those two. So compared between the polynomial versus the non-polynomial, it's just very different, right? There is a diagram. Let me show that diagram before we go into this. Okay, this is the diagram I want to show in terms of as n. So this is a plot like this on the horizontal, the x is the value of n, starting from a few small number as n become bigger. And then this line represent on each of those class of complexity, how fast they will grow, right? So this is a straight line is this ON, right? It's going the same speed as n becomes bigger, so it is a straight line, right? Those below that is O1 and log n. So it's more efficient than this linear. So those O1 and O log n, those are much better than this linear one. And then the next best above this linear line is n times n log n. Right? So it is going a little faster than the linear one. But n squared, it is way faster than n log n. And remember, n squared and then n cubed somewhere in between there. But everything n squared and n cubed and below, they are all polynomial. Right? They're all polynomial. But the n to the power n and n factorial, those are the worst the algorithm. It is exponential and factorial. Those are the worst. So as you can see, n factorial, as n get to the numbers, I don't know, you can really get out of the control, right? If, for example, if you calculate 20 factorial, that's a huge number, versus 20 for the linear, it uses 20. So just on this spectrum, you're trying to stay on the polynomial as much as possible. Then within polynomial, there is this log n below the linear and then above the linear, and this n squared, n cubed, etc. So it's still trying to stay in the polynomial, then within polynomial, trying to get to the most efficient polynomial. Right. Those above this n log n is already classified as a horrible, a bad algorithm. Right. Okay. Any question so far? Before we move on to the next topic, I think we talk about those algorithm, and then there is another classification, what's it called P problem versus the NP problem. P it's well, P is it stands for polynomial, so it's related to the polynomial algorithm type of problem versus NP. That means that you cannot find a non-polynomial algorithm to solve the problem. So it's called non-deterministic polynomial. So NP is the reason they're adding this non-deterministic. It's because sometimes you can find an algorithm to solve certain type of problem within the class in polynomial time, but it's just there is no particular rule that you can always follow to come up with a polynomial algorithm to solve this kind of problem. That's why then it's called NP problem. So in some cases you can find polynomial. In other cases, you may not be able to find. So that's why I call non-deterministic. So sometimes you can find it, sometimes you cannot. That is a non-deterministic, so non-deterministic. Then this kind of problem is called an NP problem. Right? Where a problem you can always find polynomial, then it becomes just called a P problem or polynomial problem. But if the problem, sometimes you can find polynomial, sometimes you cannot, then it becomes non-deterministic polynomial, then it becomes an NP problem. Okay. Then within the NP problem, there's sometimes you also hold this a classification called NP-hard problem. The NP-hard problem is just those NP problems, they're very difficult to solve. Okay. So NP-hard is just as hard as any NP problem, as it could be harder. So those harder NP problem is called an NP-hard problem. And then there is also another within another NP problem called NP complete. Is NP complete? That means it's already proven that problem you cannot find polynomial solution, so it becomes an NP complete. So there is some famous problem become an NP complete problem. So there is no way you can find a polynomial algorithm to solve this kind of problem. And those NP hard and NP complete, why do we care? So the reason they're talking about whether classified the problem with polynomial and or non or NP problem, and then within NP, whether it's NP complete, NP hard, you're trying to understand how hard the problem is, and so this is throughout algorithm design, whether you in high school or in college. So this is NP problem. It continues to be a problem that you want to study, how to design the most efficient algorithm to solve that kind of NP problem, whether it's NP complete or NP hard. Right? In terms of just what are those concepts, right? So so below this, there is a polynomial problem that is not NP. Then within some NP problem, there is some you can find polynomial algorithm to solve those NP problem, right? Then there is some other that you cannot. Then within that, there is an NP complete. NP complete could be within the NP problem. And then there is also NP hard problem. NP hard problem is the most difficult problem, as hard as any NP problem. Okay, let's take a 10-minute break. Okay, it's time. Hope everyone is back. Could everyone turn on the camera so that I know you're back? Okay. We will continue. So we have discussed about the time complexity. Then there is another complexity called the space complexity. Okay. Space complexity is to measure the memory efficiency, the amount of memory being used by a program. So it's and this is space complexity is very similar to the time complexity, and we can using the big O notation as well, just to measures um, how many elements that you need to store. So how many variables do you need to store? If you need to store an array based on the input, then it's ON, etc. Right? And so this complexity, obviously, you need to uh, have the input, right? You need to store the input, but as you're doing the calculation during the step, you may need to create some temporary variables that you need to store. And so the input itself, and everybody need to store that input. But there is, although there is a different way to store the input, right? You can read them all at once, store them into an array or other data structure, or you can read one element, process them, produce output, then read the next one. Then it's more efficient. You don't need to have an array to store all the input element, right? You read one, you go through the algorithm process, produce the output, then you come back and read the next one. You can, if you can do that, that is the most space efficient. And, and you have to read all the input, and as well as you have to create some array type of structure to store some temporary variable, then you will see that the memory will increase dramatically. That's why we cared about this space complexity. Right? So it's auxiliary, that means some temporary variable that you need to use, as well as space being used by the input. So together it becomes the space complexity. Okay, so the best algorithm, so trying to minimize on both sides, minimize the input space as well as some temporary variable you need to use in order to reduce the space complexity. So this is a constraint is not only because you could run out of memory on your computer. In a USACO case, they have a memory limit. And oftentimes, I think the memory limit is 256 megabytes as have the memory limit. But also, as you trying to grab more memory and then release them when you're done, that also takes time, right? That getting memory and use the memory, then release the memory, all of those will add to your runtime, not just whether you will run out of memory or not within the constraint. Even if you don't run out of memory, as you use more memory, that will add to the runtime of the program as well. So let's look at the weird algorithm. And remember this homework. So this one of the students' solution. You read the number, and then you check whether the number it is even. Excuse me. even, you divide by 2. If not, then you multiply by 3 plus 1. Then you add this number into this return string. So concatenate a space to the, right? So you store this in a temporary string variable called RET return. So you initialize this string, convert this input number into a string, and then you keep concatenate some intermediate variable that you're doing this conversion, right? Then you output this string. So what's the space complexity for this program? And because you go through this loop, right? Each time you append, concatenate this string. So this string, in terms of the memory, it will grow, right? Even though you don't need to worry about how to internally handle the memory grow this string, right? So you initialize this one is very small, and you keep concatenating to more numbers. It becomes bigger and bigger, and then at the end you output this one. So it is, in terms of complexity, or no, the space complexity is ON, right? Because we are doing this loop inside this variable, it become the bigger. Right? Does it make sense? So can we solve this problem in terms of space efficiency, improve this space efficiency? Can we make this variable constant, don't grow? Right? There is for this particular problem, we don't have to concatenate it as you calculate the intermediate number just using cout, just output it to screen instead of doing concatenate. You're building this a long string, then you output it 1. Why not just output it in time as you calculate? So this is going back to the diagram, right? You doing this preparation algorithm, when you're done, you output it once. Then you need to have more space to store it. Versus as you go through a loop, each time you output it, each time, and then once you output, you forget it. You don't need to store it. So you don't need to have that much temporary space in here. Just as you go through the loop, output, go to output. And so I will modify this program. I show you my solution. So we read this input, output immediately, right? Output inside this loop. And as we're doing the calculation, converting into divided by 2 and multiply by 3 plus 1 is odd, then output it. There is no need to store that long string. Does that make sense? So this is the mode of the space complexity. Okay, we put the time complexity and the space complexity together, and then look at some of those common data structure. So for now, just remember those names. We are going to, next week, we're going to discuss some of those common data structure, building data structure in next week's topic. For now, just you don't need to know the detail. Array in terms of the time, right? Looking at the pattern that we need to access those data structure, right? So the pattern you need to, oftentimes you need to access like getting one element, right? Access means that you're getting one element, right? And then search is the one that you don't know the position of the element, you know the value, you go through the search. This is the in terms of the time complexity, how efficient. When it's an array, right? Research, obviously, if this array is not sorted, then you go through ON, go through every element, compare the value of the element that you're looking for versus each element, whether they are equal. Then the search is ON. Right? And then insertion is when you need to insert an element to an existing array. So you insertion, that means you need to insert into the right place. So you need to find out what's the place that you need to insert. So it will take an ON time going through the search to find out the right place to insert. As well as the delete, you need to find out the right element. You know the value you need to delete. You go through the similar search, find out the position, and then do a delete. So it's an ON algorithm. Right, so that's an array. Versus the stack, a stack is a little different from array. Stack is first in, last out, right? It's like a bucket. You put it on top, and then you also pick up from the top. You just put things from the top, and then you also get things from the top, just a one way in and one way out stack. So in terms of access, so compared to array, you if you know the position, you can get that element immediately. So it's all one. Versus stack is you need to go from the top, like go to even though you know which position, you have to go through the remove all those elements at the top, go through that in order to, so the stack access is much worse compared to arrays going through ON. Right, search is similar to array, is ON, but insert, you just push an element from the top, so it's O1. And then delete as well, you do a pop, you remove an element from the top, so it's O1. So those I see different data structure have a different pattern for usage. This is there is a what they call it the average access pattern, but then it could be the worst case scenario, right? Worst case scenario in the stack, for example, you need to you need to search, not search, right? So I think in the stack they're all the same. The average and the worst are the same. But some of those data structure, the average pattern versus the worst pattern in terms of the efficiency algorithm, then the complexity are different. So I know this table has a lot of information. You don't need to memorize this. Right? We go through some of those data structure, and then we will discuss some of those access pattern in terms of those data structure, as well as some we have to write the algorithm for some data structure, for example, search. How do you search an array? Okay. And oftentimes, we probably the later part of the semester, we need to learn some of those sorting algorithm. There are a lot of sorting algorithm as well. There is quick sort, merge sort, etc. All of those are bubble sort. So we will learn some of those common sorting algorithm, and then different sorting algorithm. They have a different complexity as well. The time complexity as well as the space complexity. Space complexity, just in the worst scenario, there's a space complexity. There's only there is, so this is a more deterministic. There is no other variation, just one situation. Versus time complexity, you could have a best scenario average scenario or worst scenario. Depends on the problem. So you see some of those algorithms, they vary in terms of efficiency in the whether it's in the best scenario, what will be the algorithm, but what's the worst scenario? It could be in some cases a quick sort, for example, worst case scenario could be n square, versus the best case scenario is n log n. Okay, let's do some exercise. Let's look at this curve. So what's the time complexity for this block of code? Just type your solution in the chat. Okay, what's everyone? Kenny, what's your solution? Are you even paying attention, Kenny? What's your answer? Hello, Kenny. Okay, Kenny, can you explain why is the ON? Okay, so this loop, so ON is correct. So even though it's going through 5 times n plus 17, but we mentioned that there's a constant of multiplied by a constant or adding a constant. It doesn't change the complexity. So this is still ON. Okay, how about this one? What's the complexity for this case? It's adding a big number. Okay, so adding a big constant number, as long as a constant, then the answer is still ON. Right? Okay, so what's the complexity for this whole block of code? Okay, it's the ON square. So it's only this two nested loop as a ON square, and this is another ON, but this is n ON square, and then this ON, so we can ignore this part, just take the part that is the worst case. So the answer is ON square. Okay. Okay, how about this recursive function? And also, it's also measure the space complexity. What's the time, both the time complexity and the space complexity? Okay, Christy has the answer about anyone else. Mm, IDK. So Joel, what does space IDK mean? Oh, you don't know. Okay. Okay. So let's look at this problem. Right. We just take some example. So if I say the n is 4, we look at how it is calculated. This accum 4, it would call it again 3, 2, 1, and 0, right? So it's going through those until 0, 5 steps. So in terms of the time complexity, each time going through like a loop, going through all the way to 0. So the time complexity is obvious, it's O(n). But then in terms of the space complexity, you need to store the value of accum 0, right? Return, and then return the next, and return next. So you have also 5 elements that you need to store and return. So it's as the n become bigger, it's also the space also become bigger. So the space complexity also O(n). Okay, so in that example, right, so this code doing this recursive, the time complexity is O(n) and the space complexity O(n). Can can we rewrite this program, make it more efficient in terms of both the time and space? So first of all, we need to understand what does this code do, right? So essentially, when it's 0, returns 0. When it's 1, then this actually make a typo. This change it. This is instead of add, it should be accum. Let me correct this. Right? It called itself and then return the value. So when it's n is 1, this is 1 plus this accum 0, which is 0, so it's a 1. When it's a 2, then it's a 2 plus accum 1, which is 1, so it becomes 3, right? When it is 3, then 3 plus accum 2, we already said that is 3, then 3 plus 3, then is 6. So if we look at the pattern, it's just doing a sum of the sequence from 0 all the way to this number n, right? It's do a cumulative sum. So if you understand what it does, then you write a program more efficient than this recursive calculation. Okay, let's see, use right. So, so this is the version is doing the recursive, right? So we use a long so that we can do some big number accumulation. so we can test it, how efficient it is. In the C++, I think I showed this for those in my C++ introduction class. There is a library called Chrono that can get the computer time that can measure in microsecond. Right, microsecond is a 1 millionth of a second. Right, millisecond is a 1,000th of a second. Whereas a microsecond is even smaller than a millisecond. So microsecond can measure that in microseconds so that we can really measure how quick each time they're doing the calculation. So this is the accumulate. This is the function we want to check how efficient it is for given a number, and then we use this core accumulate, just adding this time, right? The start time and end time. So declare this two variable. So this is the type of variable. So I'm showing this example. So next time you need to measure your computer's, your program's runtime, you can copy this code. I'm going to share this code, push it into the Google Classroom. And so this start is using this function. I know it's under the chrono, there is a high resolution clock that can get the current timestamp in microsecond, right? In microsecond, this is now. So you're getting the current timestamp, then you start calling this function or cum, right? We just output this in a string, and then this call this function a value. So we are done calling this function. Then we call this computer clock again. So this is start time that the computer clock. And then after we call this function, this end time. So we have the timestamp. So then the elapsed time is just the difference between so it should be the end minus the start is the program's runtime, right? So the n minus a star is a time measured in microseconds. So because it is a clock, so we need to pass that into, convert that into, to make sure that this is in a duration measure in microseconds. So this is using this duration cast this duration into a microsecond and then call this count. So I know it's kind of weird. This is in cell just how many microseconds this actually take calling this function. Then we output this how many microseconds. Okay, so we can put in a big number, right? So we start from 1,000 all the way to this, it is 10 million. Yeah, it's a 10 million. So we do a step of 10. So from 1,000 to 10,000, then 100,000, a million to 10 million, etc. Right? So that's what this loop does. Just see if we can do the big number, doing the big number accumulation using this recursive and how much time it would take. So let's just combine the this is two version 1, and we want to output this version 1.exe. Okay. So we combine this program, then we just run this program. Okay, so it can say accumulate 1,000. So this is the answer, which is to be correct as accumulate sum of those number, and then runtime is a 201 microsecond. And as we increase this to 10,000, it becomes 209 microsecond. And so probably it doesn't increase much, even though this input increase 10 times. But if you look at the next one, this become 100,000. You see this time increase almost 10 times as well. So the runtime, it goes linear. So it's definitely an ON time. But then what's this segmentation for? Remember earlier, I mentioned that as you call this recursive function many times, which we do the next, right? This is 10,000. This is already 100,000, right? 100,000. The next we call it 1,000,000 times. Then it just ran out of memory. This memory stack for keeping track of this recursive function. It's not a memory of the whole computer. This has some allocated, dedicated memory to keep track those recursive function. So that part is running out of memory to become segmentation for. So that's a problem with a recursive function. One, it's the ON, right? It's the increase in terms of as n become bigger, the runtime getting bigger, and you can also getting the out of memory become segmentation for. So how do we rewrite this program using the don't use a recursive, using something else? So one way to not using the recursive, just use the loop, right? We know how to calculate the accumulator. So let's look at the second version, right? So given a number, we just need to accumulate the sum, go through each element. This is sum, right? Just add it to the, just using a loop. So this, in terms of the time complexity, this is the ON, right? So we're doing a one-time loop. So we copy the same. This doesn't need to be changed. So it's called as a function. So this is something probably next time you can copy, just need to change this function that you call, then you can measure in terms of how many microseconds that function call that will take. You pass the argument from here. Oh, instead of in, we should change this to long as well. Okay. So it's to be consistent, this using long, so that we can handle large number. So everywhere, including this loop number, right? This a long, also using long, so that we can handle a large number. And similar in the main function, we just call this a same type of call. We start from 1,000 and then increase, multiply by 10, so until it reach 10 million. Okay, let's compile this program. So this is version 2 and version 2.exe. Okay, now let's execute this program and see what happened. Now, first of all, we are not getting that segmentation for a problem. So we're able to calculate from 1,000, 10,000, 100,000, 1,000,000, and 10 million. So those accumulation numbers, those are the correct answer, right? And then you look at the runtime, right? From, so this is 52 to 28. This is probably something just because of starting executed is the computer need to doing a cache situation, so that it would take some time. So when it's the second time they execute, this actually doesn't become faster. So that's why I think getting, because they're using the cache. But from this second case onward, from 28 microsecond to 273 microseconds. So it's about 10 times longer. As this n become 10 times bigger, right? Then the next 10 times bigger, this is in the 2000 range microseconds. So there's a runtime also in the 10 increase 10 times. And then we increase another 10 times, then this runtime is increase another 10 times. So you can see as the n become bigger, your runtime become bigger linearly in the same proportion. So this is a good example to show you the in actual runtime that increase in the ON time. Okay. So compared between these two, right, in terms of the efficiency, if it's just the time it can handle, it's about the same. But then this recursive function getting to an issue when this calling many times, we're getting to 1,000,000 time of a recursive function that you're getting segmentation for. So in the future, if you're going to execute the program like up to 1,000,000 times, then definitely no, you don't want to write any recursive function. Convert the recursive into a loop. Okay, so even though this loop, it is better than the recursive in terms of the not getting the segmentation fault, but still not very efficient. Right? Can we make it more efficient? Right. Well, first of all, in terms of the actually this loop, there is another advantage compared to the recursive. Right. So remember, recursive, you need to allocate memory for each of the recursive variable, versus when we do the accumulate, we just using single variable sum, accumulate the sum, just keep accumulating. We are not allocate additional memory. So this sum is just a constant. It doesn't grow as this n become bigger. So this in terms of the space, this is actually the O1 versus the recursive is the ON. This is using a loop. Then this space complexity being reduced, so from ON to O1. Right? But the time complexity is still ON. Can we improve the time complexity? Anyone? Any idea there? I see this is such a simple calculation, but as we doing this millions and millions time, it's still taking time, right? This in terms of microseconds, it increasing based on the input number. Can we? So there is, in terms of the efficiency with the ON, there are other algorithms that O log n, if we can get into the O log n or O1. Those are the two type of algorithms that are more efficient than ON. Can we, for this particular problem, can we design an algorithm either in O log n or O1? Okay, so if you Okay, so we already talk about this right there do the for loop, then the space complexity is O1. But if you look at this accumulative sum, so if you remember, let me do a new. So do you remember what's the, so essentially we are doing this calculation, right? All the way to n. But for those, if you remember in your math class, is that a formula instead of going through a loop to do this sum? Is that a way? Calculate this sum without a loop. Is there a formula? Right? Essentially, we start from 1, then add it to 2, we're doing a loop, right? So can we get this accumulated sum without going through the loop? Anyone? Okay. No? Okay. So if the sum is there, right? Isn't the sum equal to? So you see the pattern m plus 1 and then m plus m minus 1. So they are in a pair. So the pair is m minus 1, m plus 1 times half of them. So n divided by 2. So that's the formula for this sum. So we don't need to go through this loop. Just calculate this formula. Right? So instead of going through a loop like this, you just do a one calculation. We know this n. Why do we need to go through a loop? So that's the math behind this. So there's a way to do a loop, or you don't need to do a loop. Just now you know this problem. It's just to calculate this formula. So let's see. So the version. So we check of this accumulated function. If it's less than 0, so just make sure the boundary condition is 0. And if it's greater than 0, then we use this formula. Just return this. There's just one calculation, no loop. So in terms of the efficiency, then this is O1. Okay, so we use this call accum same, keep track the time. This is same, and this main function also identical. Okay. Now let's compile this. Okay, now we execute this program. Let's make this terminal bigger so you can see the runtime we had before, right? With in terms of compare this version 2, those are runtime in how many microseconds. Let's see. See, so far, everything is almost 0 second. This is just the first time because they're running one. See, as n increase, the runtime is almost no time at all, 0 second. See, that's I'll tell you in terms of the algorithm design, right? How can we design an algorithm from here to here? So This O1 algorithm, that's the ultimate most efficient. It's almost no time that at all. So it's even this in microsecond, you cannot measure it. It's almost 0 microseconds. And it's amazing. So that's why in the computer program, this is there are a lot of situations like this when you can avoid loop. If you can avoid loop, you know the formula to calculate do the calculation without the loop. Just come up with the formula to do the calculation without the loop, and then we're getting the same answer as well, right? For this program, then the time complexity is O1, and then space is also O1. And we already see this. Okay, any questions for today's class? That's all for today. Right? But no question, we can end this class. Thank you, everyone.